This lecture introduces Chapter 6, Terrestrial Worlds in the Inner Solar System. In this chapter, we will look at terrestrial planets Mercury, Venus, Earth, Mars, and the Moon, and we will use comparative planetology to understand the worlds of the inner solar system. We will also look at the processes that affect the interiors and surfaces of terrestrial worlds. Comparative planetology is the systematic study of the similarities and differences among planets, with the goal of obtaining deeper insight into how the solar system formed and has evolved in time. The orbital semi-major axis is the average distance the planet is from the Sun. For the Moon, it is the average distance from the Earth. The orbital period is the time in years for a complete 360-degree circuit around the Sun, and for the Moon, it is the time in days to go around the Earth. The orbital velocity is the average speed as the planet goes around the Sun or the Moon around the Earth in kilometers per second. The mass is given in terms of Earth masses. The equatorial radius is given in kilometers and in terms of Earth radii. Since none of the objects are perfect spheres, we need to differentiate between the equatorial and polar radius. The Earth's equatorial radius is 6,378 kilometers, but its polar radius is 6,356 kilometers. Due to the fact that it rotates, it gets a little bit squished. The density, mass divided by volume, is given in terms of density of water. The density of water is 1 gram per cubic centimeter at 4 degrees Celsius. The rotation period is the length of a day on a planet in days. The tilt, obliquity, is given in degrees. The surface gravity of an astronomical or other object is the gravitational acceleration experienced at its surface. Historically, on Earth, the acceleration of gravity is a measured quantity. It is 32 feet per second, or 9.8 meters per second squared. Newton's law of gravitation can predict the surface gravity on any object if the mass and radius are known. Performed in 1797 and 1798 by British scientist Henry Cavendish, was the first experiment to measure the force of gravity between masses in the laboratory, and the first to yield accurate values for the gravitational constant g. The escape velocity is the speed that an object must reach to escape the gravitational influence of Earth. The escape velocity is different for different objects and given by the square root of twice the gravitational constant times the mass of the object divided by the distance from the center. For Earth, escape velocity from the surface is where little r is the radius on Earth is 11.2 kilometers per second. If you could launch a ball straight up from the surface with a velocity of 11.2 kilometers per second or greater, it would not fall back to Earth. To escape from the surface of the Sun into interstellar space, the escape velocity is 617 kilometers per second. However, from the orbit of Earth, it only takes 42.1 kilometers per second to escape the influence of the Sun into interstellar space. So far, 5 space probes have been launched with or have acquired sufficient velocity to escape the Sun. Pioneers 10 and 11 launched in 1972, Voyagers 1 and 2 launched in 1977, and New Horizons launched in 2006. Contact has been lost with Pioneers and with Voyager 2, but NASA still communicates with Voyager 1. It is 19 light hours away. It takes 38 hours for a signal to be transmitted from Voyager 1 and a reply received. Voyager 1 has officially left our solar system. It's the farthest any object has been launched from Earth. This graphic shows the relative positions of NASA's most distant spacecraft in early 2011. Looking at the solar system from the side, Voyager 1 is the most distant spacecraft, about 17.5 billion kilometers away from the Sun at a northward angle. Pioneer 10 is the next most distant, about 15.4 billion kilometers away from the Sun, on the opposite side of the solar system. Voyager 2 is about 14.2 billion kilometers away from the Sun on the southward trajectory on the same side of our solar system as Voyager 1. Pioneer 11 is about 12.4 billion kilometers away from the Sun, and New Horizons is about 3 billion kilometers away from the Sun on its way to Pluto. Voyager 1 is now 20 billion kilometers away from Earth, and Voyager 2 is 16.8 kilometers from Earth. New Horizons is well past Pluto and on its way to rendezvous with Kuiper Belt Object 2014 MU69 in January 2019. Voyager 2 was launched with a speed relative to the Sun of less than 35 kilometers per second, passing by Jupiter, Saturn, Uranus, and Neptune in a so-called slingshot orbit. The Voyager spacecraft acquired additional speed, easily surpassing the escape velocity. New Horizons was launched from Earth with a speed of 45 kilometers per second, the fastest any object has been launched from Earth. It only flew past Jupiter, which gave it a modest increase in speed. It still has enough speed to escape from the solar system after it passed Pluto in the summer of 2015. The closest major body is the Moon. The Moon's surface is heavily cratered. Craters are typically about 10 times as wide as the meteoroid that created them and about twice as deep. Rock is pulverized to a much greater depth. Big lunar craters date back to at least 3.9 billion years ago. Much less bombardment has occurred since then. Regolith is the lunar soil, the thick layer of dust left by meteorite impacts. The Moon is still being bombarded, especially by small micrometeorites. This softens features, but other than impactors and 12 people walking around it for a few days, not much else has changed the surface of the Moon. The near side of the Moon refers to the side that is constantly facing Earth. Since Earth's Moon doesn't have a significant atmosphere, nothing can stop even the smallest meteoroids from striking its surface. As a result, the lunar surface is heavily cratered. As a matter of fact, tiny craters are quite often even on lunar rocks. This was observed on the moon rocks brought home by Apollo missions. The absence of liquid water on its surface has allowed the Moon to preserve much of its ancient geological features. Other prominent geological features found on the surface of the Moon include maria, rills, domes, wrinkle edges, and gravens. The most distinctive aspect of the Moon is the contrast between its bright and dark zones. Lighter surfaces on the lunar highlands, which receive the name of terrae, and the darker plains are called mare from the Latin word for sea. The maria, which comprise about 1/3 of the Moon's near side, are made up of flows of basaltic lava formed from volcanic activities that occurred in the younger years of the Moon. The highlands are anorthositic in composition, whereas the maria are basaltic. Rills on the Moon sometimes resulted from the formation of localized lava channels. These generally fall into three categories, consisting of sinuous, arcuate, arcuate or linear shapes. By following these meandering rills back to their source, they often lead to an old volcanic vent. A variety of shield volcanoes can be found in selected locations on the lunar surface, such as the Mons Rumker. These are believed to have been formed by relatively viscous, possibly silica-rich lava erupting from localized vents. The resulting lava domes are wide, rounded, circular features and gentle slope rising in a few hundred meters at the midpoint. They are typically 8 to 12 kilometers in diameter, but can be up to 20 kilometers across. Some of the domes contain a small pit at their peak. Wrinkle edges are features created by compressive tectonic forces within the maria. These features representing buckling of the surface and form long ridges across parts of the maria. Some of these ridges may be outlined buried craters or other features beneath the maria. Grabens are tectonic features that form under extensional stresses. Structurally, they are composed of two normal faults with a down-dropped block between them. Most grabens are found within the lunar maria near the edges of large impact bases. The surface of the Moon has been subject to billion years of collisions with both small and large asteroidal and cometary materials. Over time, these impact processes have pulverized and hardened the surface materials, forming fine grains layer called regolith. The thickness of the regolith varies between 2 meters beneath the younger maria and up to 20 meters beneath the oldest surfaces of the lunar highlands. Mercury has long thought to be tidally locked to the Sun. Measurements made in 1965 showed this to be false. Rather, Mercury's day and year are in a 3-to-2 resonance. Mercury rotates 3 times while going around the Sun twice. Mercury can't be imaged well from Earth, and the best pictures have been obtained from the Messenger spacecraft. Cratering on Mercury is similar to that on the Moon. Mercury exhibits some distinctive features called scarp or cliffs, which are several hundred kilometers long and up to 3 kilometers high. They are thought to be formed as the planet cooled and shrank. Caloris Basin is a large impact feature ringed by concentric mountain ranges. Before radio observations in the 1960s, many believed that Venus contained a lush Earth-like environment. This was due to the planet's size and orbital radius, which suggested a fairly Earth-like situation, as well as thick layer of clouds which prevented the surface from being seen. Among the speculations on Venus were that it had a jungle-like environment or that it had oceans of either petroleum or carbonated water. Because of the lack of features, direct observations of Venus's rotation rate could not be made. Later observation in 1962 revealed a rotation rate about 240 days. The modern value is 243.025 days. All of the planets in the solar system orbit the Sun in an anti-clockwise direction as viewed from above Earth's North Pole. Most planets also rotate on their axes in an anti-clockwise direction, but Venus rotates clockwise in retrograde rotation once every 243 days, the slowest rotation of any planet. Every 584 days, Venus completes an interior conjunction where it lies between Earth and the Sun. It is at this point that Venus makes the closest approach to Earth of any planet at an average distance of 41 million kilometers. This map of the surface features of Venus is on the same scale as the Earth map below it. This picture was imaged by the Magellan orbital spacecraft. Using radar, Venus's surface appears to have been shaped by extensive volcanic activity. Venus also has several times as many volcanoes as Earth and has 167 large volcanoes that are over 100 kilometers across. The surface of Venus exhibits lava domes and shield volcanoes. On the left are lava domes on Venus, and on the right is the volcano Gula Mons. In 1981, the Soviet Union landed 2 spacecraft on Venus, Venera 13 and Venera 14. The Venera 13 lander survived for 127 minutes, and the Venera 14 lander for 57 minutes, where the planned design life was only 32 minutes. The area was composed of bedrock outcrops surrounded by dark, fine-grained soil. Almost 1,000 craters exist, which are evenly distributed across the surface and range from 3 kilometers to 280 kilometers in diameter. Meade's crater on the right is Venus's largest crater. No craters smaller than 3 kilometers exist because of the effect of the dense atmosphere on incoming objects. The surface features easily seen in a telescope, and the rotation rate was easily established for Mars. In 1894, Percival Lowell, related to Lowell of Lowell, Massachusetts, viewed Mars with one of the largest telescopes then available. Lowell thought that he saw canals on Mars. He theorized that an advanced but desperate culture had built the canals to tap Mars's polar ice caps, the last source of water on a drying planet. Lowell was merely observing projections of the vein structure of his own eyeball, an optometrist believes, a known nuisance among planetary observers using very high magnification. This would explain, among other things, the phenomenon's consistency across two far-flung planets in our solar system. In summary, the inner planets are the terrestrial planets. Four processes shape the surface of terrestrial planets: impact cratering, volcanism, tectonics, erosion from wind and water. Arguably, life also shapes the surface of a planet. Comparative planetology is the systematic study of the similarities and differences among planets with the goal of obtaining deeper insight into how the solar system formed and how it has evolved in time.